Back then to our final topic for tonight. These two topics, we'll roll them into one. To date, we've been kind of focused on getting you up to speed with the language, getting the principles of test-driven development on board, and we've also been trying to evolve our understanding of some of the core principles of software development through examples, really. But we need a little bit more than that, and these set of principles here are a useful tour of the decisions you make on a daily basis as you are evolving the structure of an application. It's a fairly well-respected set of principles originating from the 90s. It's surprising really how many years old many of the core technology we're using today is. This is a quite influential book, and there's a whole series of papers and even some conferences around this suite of principles. They've stood the test of time reasonably well. They've been supplemented, of course, by other ways of composing classes and determining object structure, but they are pretty useful introduction to the whole field. And the principles themselves, characterized as 5, and they look a little bit obscure when you have first contact with them. SRP, OCP, LSP, ISP, DIP, they seem a little bit technical, and some of them are in fact a little bit challenging to get your head around, but they're mostly common sense, and common sense from a class designer's perspective. We're just looking at one today, SRP, single responsibility principle, the idea that a class has one thing to do, or more importantly, one reason to change. The idea is the classes remain focused and are resilient to shifting requirements. Open-close principle, or OCP, is focusing on how we modify existing systems, in particular the role classes play in this. The core concept of OCP is that we can extend without breaking systems. And when we look at OCP, I think you look at it next week, you'll be seeing it, how we do that in the Java context. LSP is central to how modern OO systems work, in particular about how interfaces and inheritance work, and specifically how we can ensure that we can introduce a degree of substitutability into the classes we evolve. ISP and DIP are a little bit more orthogonal to the above 3. They focus on how we organize dependencies and how those dependencies achieve a certain appropriate range of granularity, granularity that can keep our system robust and cohesive. Somebody had a bit of fun with these a couple of years ago. The idea is that if we're not applying these principles, our application can be quite fragile. It becomes a tower of Jenga bricks. Move one thing and the whole thing comes down. Anybody who's worked in software, I think, is familiar with that queasy feeling. Maybe you had that feeling during your assignment. SRP, just because you can doesn't mean you should. Swiss Army knife could look like this, be fun to do, would be very challenging to use. And this SRP, which we'll look at in a moment, talks about responsibilities of classes and tries to equate or draw a link between those responsibilities and reason for change. And the reason for change really is the thing that SRP focuses on. If we can identify these axes of change, then we can start to uncouple class responsibilities, make them into independent classes, and thus change has a less disruptive effect. We'll see that in action shortly. Open-close principle, well, this is a kind of a bizarre poster. Open chest surgery isn't needed when putting on a coat. Seems a bit over the top. But the idea here is that we are using mechanisms like subclassing and polymorphism to be able to introduce new features rather than opening closed systems. A notorious source of errors in the industry has been systems already deployed in the field, running for many prolonged period. Maybe they've had their problems, but they continue to operate. New features required, opening the system, dangerous. Open close principle discusses how we can extend the system but keep existing code in place and maybe even keep existing upstream dependencies in place on those systems. LSP looks like a duck, quacks like a duck, but these batteries, you probably got a wrong abstraction. Okay, that's a very nerdy type joke. But you've seen a bit of that in action already. In the sample solution, we have a console class, and we also have an ASCII table console class. I think we might have called it ASCII table parser. One is subclass of the other. We should be able to replace one with the other without any side effects. That is, in this particular case, we introduced the ASCII table capability into a class which replaced or augmented an existing capability. These are a little bit more obscure, and we'll take a little bit of time to look at them a bit later. Interface segregation principle. And the idea here is that we try to make fine-grained interfaces that are maybe specific to the clients they're using. Again, cutting complexity and starting to make the interfaces in the system a little more explicit and a little more tuned to potential clients. And dependency inversion principle, it's kind of hard to get at the first point of contact here. Would you solder a lamp directly into the wiring on a wall? Well, you wouldn't really. You would, of course, have your lamp use a plug and the electricity system to support the plug standard, and the electricity system and the lamps and all other appliances would collaborate and use that abstraction, if you like. So we shouldn't have held on low-level modules, shared abstractions, and then we depend on these abstractions, not concretions. We don't develop lamps that will be wired directly to all sorts of different electrical systems. They have a plug, and the plug plugs in then to conformant systems. So there are the 5 principles. There have been 2 or 3 other added since, which we'll hardly have time to look at. You'll probably be able to feel around for them. They're language independent, more or less. They apply to all systems. In fact, the original text introduced them, I think, explored them in the context of Java and C++ and other languages. And other languages may augment them specifically when considering the challenges that those languages pose. Let's take a deeper look, though, at them, because I've just glided over them, really. Let's look specifically at this one, SRP. What does it mean? What does it do for us? Putting it as succinctly as we can, there should never be more than one reason for a class to change. And we regard these as responsibilities, and responsibilities are an axis of change. If our system is not susceptible to change, if the requirements will never change, or if the underlying computing resources it accesses to won't change, then this principle is largely irrelevant. But of course, we are aware that change is a fairly permanent feature of software development. And SRP tries to embrace change, try to understand change in a bit more subtle and detailed manner, and try to incorporate an ability to resist, perhaps not resist, but to cope with change in a more intelligent manner. And SRP is focused specifically then on the aspects of looking at the responsibilities of classes and keeping those class responsibilities cohesive, so that changes are isolated between classes and not a disruptive force. Some very simple-minded examples. A report class has got to acquire report data, assemble a report, modify the format, and then maybe print it. Okay, I'm not showing any data flowing into this or any parameters for these methods here, but you get the idea. The class is encumbered with responsibilities around building the report from the raw material, formatting, and then printing it. SRP would say, well, that's too much, pull that apart. Maybe there's a strong report abstraction, a class on its own, and maybe there's a report generator or some other more suitable name. Each one has a specific responsibility then. The content of the report in one case, and the format or formatting of the report in the other case. Two different axes of change, because the report format can of course change without any reference to the content, and vice versa. Another example, we might have a rectangle class, and the rectangle class has things like draw or render, and it also has maybe things for computing the area or other transformations perhaps of the geometry of the class itself. It seems like a reasonable thing to put into a class on first thought, and maybe it works well for a small application. But as soon as we have consumers of the class in action, things might get a little bit more complicated. Geometry application, maybe using the class purely for its geometric features, just wants to do some calculations, transformations, or maybe it's matrix manipulation going on here. Graphical application is interested in something else. It wants to render the rectangle onto a graphical user interface and is introducing the machinery to do that binding. We'd say these classes, particularly the rectangle class, is violating SRP, particularly as we consider the type of use cases that might arise. It becomes encumbered with two different things: the management of the data structure, and then the interaction of data structure and its rendering onto a graphical system. The geometry application has got to haul around with it the entire GUI graphical application, even though it only wants to use the core transformational features. Similarly, the graphical application maybe is not that interested in transformations and still has to carry that interest with it. If we were to pull those apart into a geometric rectangle and a rectangle, giving them different responsibilities, then we have a more cohesive system, more robust, more likely to survive major changes. The GUI system is being updated, then we're only going to be updating the rectangle class. If we've got new transformation algorithms we want to experiment, maybe new coprocessors or whatever, maybe a new matrix transformation library, then we're only introducing that into the geometric rectangle class. The original rectangle class with these merged responsibilities is no longer there, and we have an independent line of change and evolution for these two classes. You can see SRP is kind of common sense, really, and it's a natural tendency of developers as they're putting classes together to think along these lines. Another one, a modem. These are a lot different now to what they used to be, but let's imagine dialing and hanging up and sending and receiving characters. That looks reasonably cohesive and coherent. We think we'd be happy enough with that. It kind of mirrors the modem box itself, if such a thing exists anymore. But if we examine this little specification from the change perspective, then maybe we reconsider. There's two different reasons for change here in how this modem is structured. One is connection management, and the other is data communication. Connection management, dial and hang up functions, is associated really with a whole sphere of technology to do with signaling, and data communications is to do with transmission. And they may have different reasons to change. There may be different protocols involved in signaling that are independent of the transmission itself, or transmission itself has got to consider a range of different lower level requirements, including particularly framing and speed and so on. These change for different reasons. then we say this responsibility principle comes into play, and maybe we start to pull them apart. The data channel interface and the connection interface, perhaps. Now, if we're using interfaces and classes implementing interfaces, we may still choose to have one class implementing both interfaces. So there's interesting dimensions here to applying this principle, in that we are keeping the interfaces separate, but maybe the implementation needs to stay coupled because of complexity reasons. So we still have one class implementing it, but the responsibilities of the class are a little bit clearer and maybe segregated. Another example, employee object, calculate pay, store the employee. Simple one again. Why should we have persistence or database management in the same class as something that calculates pay? Pull those apart, and we have something we can evolve independently. Calculate pay obviously has a range of other interesting algorithms that has to be computed. Employee DB, well, that's got a different set of concerns we maintain separately. Let's take one more example, and then we'll have a quick reflection on our assignment solution, just to think about it in terms of responsibilities, and you might start to think along these lines for your assignment 2 as well. Let's say we want a contact list to be managed. That is an address book, let's say. Address book, contact list, got to have a user interface, load save from disk, reports, and search functions. Might end up with a class contact, obviously. We need many contacts in our system, and the address book class seems to make sense. The address book will load up the contact from disk or from database, will allow you to search it, provide the UI, and a whole other range of features. You could see us jumping into such an implementation reasonably easily, but you can see also how the address book class is starting to already accumulate pretty significant range of responsibilities. Managing a data structure, you've seen what that's like. Serialization, well, you've also seen how complex that can be. Reporting, command line itself, and that's not even to consider the whole user interface or user experience. Clearly, we could do it. We could have this Swiss Army knife with incredible capabilities in the address book, or we could start to pull it apart. Using our judgment, our experience, our applications we developed as type in the past, we might come up with a range of interfaces that encapsulate the key behaviors, and then we might implement them in various classes. So contact class, contact reporter, serialization, address book itself is still in there, but now it's doing a lot less. A PIM, personal information manager class, may have to be invented to bind the address book and the associated user experience. And then maybe there's an application class as well out at the far side. Again, listing out possible responsibilities here in terms of simple statements that we can reason with and that we can communicate clearly to others who may be building or working on a system like this. These responsibilities then are hopefully coherent. They're oriented around possible change axes, and when and if those changes occurs, those changes are isolated to the individual classes that bear those responsibilities. So if a new persistence mechanism is used to be incorporated, or if a new data structure is to be included, then we're going to one class which is managing those concerns. If a new report format is required, again, there's a class dealing with that, not a fat class, as it's sometimes called, that has to cope with this full set of dimensions. Back to where we started, your assignment solution. We ended up with 3 packages: models, utils, and controllers. Let's just do a quick summary of the responsibilities we ended up incorporating into those classes. First of all, we can also conceptualize responsibilities at the package level. The models is the information model for our app. It's a very common pattern to have a models package in an application. So almost expected now really for a broad range of applications. We know we go in there, we're looking at the core information model. Controllers is a name we've given to our general services plus our user interface. Perhaps a little bit too much going on in there, but particularly our user interface might reasonably be decoupled from that package, but that's a command line application, so it's fine. Utils, general purpose utilities. Ideally, general purpose utilities should be exactly that. That is, they don't care about the application they've been included into. That is, there should be no dependencies from utils to our application. That's not quite true in the way you've implemented it, and I'll call that out as we go along. This is our models. User activity location. This is the easiest one, I think, to see SRP principle in action because they're representing individual users, activities, and locations. The responsibilities are fairly clear cut here. Now, that doesn't mean there's room for improvement, and it doesn't mean we can reflect a little bit on the equipment we've installed into these classes. And in fact, you might notice they tend to be, these simple models tend to be a little bit verbose occasionally. That's largely because of the boilerplate we need to equip model classes in the context of traditional Java development. One of the things you will be surprised at when we look at Kotlin is how these models become much more concise and more attractive to manage. And you'll see us removing large amounts of very repetitive code. This is our utils package as we delivered in our assignment. Serializer, XML, JSON, and many of you did the YAML one. A console, an ASCII table console or parser, and then formatters. The idea here really is that each of these classes takes on specific responsibilities that we can manage independently, as we've discussed. The time formatters is a clear one, really. Centralized datetime formatting for an application. Datetime formatting, as you know, is a challenge. You don't really want all your management of the formats scattered throughout your application, because if you ever need to change it, you're in trouble. If you're changing, obviously, things like locale specific